Hi everyone, I'm Sarah Jabor, an incoming PhD student at the University of Michigan studying computer science, advised by Professors Jenna Weens and David Bowie, and working closely with Drs. Ella Kazzaruni and Michael Schoding, physicians at Michigan Medicine. I'll be talking about our work, deep learning applied to chest x-rays, exploiting and preventing shortcuts. Deep learning has shown promise in the automated diagnosis of disease based on chest x-rays. For example, there are systems that can take as input a chest x-ray and produce the probability that a patient has pneumonia. However, the availability of data alone does not necessarily ensure good generalization performance. For example, suppose you have a set of patients, males and females, and we want to teach a system whether or not these patients have heart failure. So we train a deep learning model based on their chest x-rays. Applied to our test set from the same hospital, it looks like the model does great in correctly classifying them. Now our colleagues at the VA are excited to try out our system. They apply our model to their patient population, but it fails miserably. It classifies all of their patients as negative for heart failure. So what happened? In this toy example, the model capitalized on a spurious correlation between sex and heart failure by taking a shortcut. Based on the skewed training data, it learned to look at the features of sex, such as breast tissue, and ignored the clinically relevant features of heart failure. Our goal is to build a system that doesn't rely on these features, but rather on the features of heart failure. Beyond sex, we showed that deep learning models can map to a number of attributes, including BMI, age, or the presence of a pacemaker from chest x-rays. So, when these attributes are correlated with the outcome of interest, a model can use them as a shortcut in its prediction. One bit of good news is that if you have access to a training set for a similar disease where this bias isn't present, a simple transfer learning approach is surprisingly effective. Given a chest x-ray as input to a deep network modeled by an encoder and final linear layer, the approach first learns all of the parameters on the network on an unbiased source task, in our case, pneumonia. We then freeze the encoder parameters and tune only the last layer on the target label with biased data. This mimics how a clinician might reuse common features, such as the presence or absence of fluid in the lungs, for different diagnoses. We compared to training various amounts of layers and different initializations, but found that this approach worked the best. For example, if you train all the layers of a network with biased data for CHF towards sex, CHF AUROC is only slightly better than random. However, with proper initialization and pre-training on an unbiased source task, we see significant improvements in performance with an AUROC of 0.73. While transfer learning is a well-explored area, it is a surprising result that the last layer simultaneously has the capacity to learn an expressive model, while also not enough capacity to overfit to the bias. More details can be found in our paper. Thanks for watching.